So we already looked at Snell's law. We saw that sine of theta 2 over sine of theta 1 is equal to n1 over n2. But I said we would expand upon that because that version of Snell's law is a little bit limited in that it only takes into account angles relative to the normal and the indices of refraction. When we're dealing with light, we can certainly talk about speed, we can talk about wavelength. What we'd like to do is we'd like to also incorporate that into Snell's law. So when we're talking about the wave model of light, we are talking about light being a transverse wave. And one of the things that we want to recall from Physics 20 is that when light passes from one medium to another, its frequency does not change. Because you got to keep in mind, the frequency of light is dictated by the source where that light is produced. So that is not going to change regardless if light travels from air to water to whatever. Like if I have a green laser pointing in the air and I shine it in the water, yes, it will have a different color when it's in the water just because of refraction, but that doesn't change the fact, it doesn't change the actual source. Like it's still a green laser pointer at the end of the day. So kind of going back to our universal wave equation, if we have v equals f lambda, well, if the frequency stays constant, that means v and lambda have to change kind of in step with one another. So like for example, if v goes up, wavelength goes up. Speed goes down, wavelength is going to go down. So this is an idea that we want to use when we're looking at Snell's law. Now, there's some geometry and some nice proofs on this. Again, in the years past, I've done this to kind of highlight it to students. I found it they didn't really care about it. So I'm just going to present without proof kind of an expanded form of Snell's law. So the expanded form of Snell's law, and on the data sheet, you'll see it split up into two equations. So we have this n2 over m1 equals sine theta 1 over sine theta 2 that we've already seen. But we also have this n2 over n1 is equal to v1 over v2 equals lambda 1 over lambda 2. Now keep in mind, we could also say that sine theta 1 over sine theta 2 equals these two parts. Basically, in these two equations here, we can actually make 6 different equations out of them. And of course, we have everything defined. So n1 is our index of refraction, our incident medium. n2 is the index of refraction, our refracted medium. Theta 1 is our angle of incidence. Theta 2 is our angle of refraction. So v1 is going to be the speed of light in the incident medium. v2 is going to be the speed of light in the refracted medium. Lambda 1 is going to be the wavelength of light in the incident medium. And lambda 2 is going to be the wavelength of light in the refracted medium. So we have a lot of equations in here, but again, it's a really powerful tool and it opens up more with Snell's law. And then from this equation, we can actually derive this whole n equals c over v. Like if I kind of look at this n2 over n1 is equal to v1 over v2. When we're doing n equals c over v, we're usually talking about, light going from vacuum to somewhere else. So if I talk about 1 kind of being a vacuum, 2 being a non-vacuum medium. Well, let's look at this. N2 is going to be the index of my non-vacuum medium, so N2. N1 is just going to be the index of my vacuum. And then the speed of light in a vacuum is just going to be c. And then we have this speed of light in our non-vacuum medium. Well, N2 divided by 1 is just going to be N2. C divided by V2 is not going to change. Let's just drop the subscripts, though, so we could just say n equals c over v. So in a pinch, if you don't know where n equals c over v comes from, you can absolutely get that from Snell's law. So let's look at this equation. Let's look at Snell's law in a bit more detail. So as always, we like to introduce these graphical questions because these always come up on the diploma exam. They kind of help to compensate for the fact that you're not really able to do a lab or do a lot of lab-based stuff on the exam. So let's look at what's going on. So in an experiment to find the index of refraction of an unknown medium, a student is going to shine a laser light from air into an unknown medium. So we know N1 is going to be 1. We don't know N2. So by varying the angle of incidence, the student is able to determine how the angle of refraction responds to this change. So we have a graph of sine of angle of refraction versus sine of angle of incidence. So I have sine of theta 1, and I have on the x-axis here sine of theta 2. So using graphical analysis, we'd like to find the index of refraction of the second medium. So we're looking for N2. So we have n1, we want to find n2, we know sine theta 2 and sine theta 1. So the equation that's going to help us out here is going to be Snell's law. So Snell's law, we know sine of theta 2 over sine of theta 1 is going to be n1 over n2. Now, when we're doing all of these graphical questions, we always want to be really careful. We want to make sure that we isolate for what's on the y-axis, and we want to separate what's on the x-axis from everything else. So on my y-axis, I have sine of theta 2. What I want to do is I want to get sine of theta 2 on its own. So I know that sine of theta 2, that is going to be n1 sine theta 1 divided by n2. So that covers me for that. I got y equals something. The second part is we want to take what is on our x-axis and we want to separate that from everything else. So sine theta 1 is the special piece. It's on our x-axis. So we want to kind of separate that from everything else on the right side. So I could put this n1 over n2 in brackets. And then I have this sine theta 1. Sorry, this should be sine theta 2. So now I have y equals something times x variable, and then plus or minus nothing. So in this case, our y-intercept should be 0. Now we can relate this to the form y equals mx plus b. From the graph, we're told that this is our y variable, and from the graph, we're told that this is our x variable. What this tells us here is that the slope of that graph, it's going to be equal to the ratio of n1 over n2. Now, what we would like is we would like to find n2. So we know that n2 is just going to be n1 divided by the slope of the line of best fit on our graph. So this is the first major part. We want to actually get that. We want to actually get sort of this graphical analysis set up. The second part, the more labor-intensive part, we actually have to find the slope of the line of best fit. So we're going to go up to our graph here. What we'd like to do is we'd like to find 2 points that are easily identifiable on this line of best fit. Now the points I choose versus the points you choose, they may be slightly different. So I'm going to choose this end point here because it looks pretty easily identifiable. So I'm going to say that's the point 0.520 and 0.350. And I need to find one more point that I can easily identify. We try to pick them far apart from each other. This point looks pretty easy, 0.220 and 0.150. So these are my 2 points for the slope. So I have my x1 and y1, I have my x2 and my y2. What I'd like to do now is I'd like to actually find the slope. So we know that the slope is that y2 minus y1 over x2 minus x1. So let's calculate that slope. So we got 0.350 minus 0.150 divided by 0.520 minus 0.220. So for this slope, let's see what we get here. We're going to get 0. So we're going to get about 0.667. Now, there's no units on this. There's no units up top, no units on the bottom, so this is just going to be a dimensionless number. So having a slope of about 0.667, we know that n2 is going to be n1 divided by our slope. So n2 is n1 divided by the slope. Well, we're told this thing starts in air, so we know n1 is just going to be 1. So we're going to have 1 divided by this slope of 0.667. So this is going to give me about 1.50. So I'm going to say, using graphical analysis, the index of refraction of my second medium is about 1.50. What it is, who knows? Something like this is generally something you would do in a lab. Like, we would give you some way to like measure angles of incidence, angles of refraction, in order to have you determine an index of refraction. But it's a little hard to do a lab without the equipment. But yeah, this is just another graphical analysis question, just again to show you and highlight that methodology. So we're just going to do one more really quick Snell's law question. So let's see what we got here. So we got light. It has a wavelength of 737 nanometers. It's going to enter quartz glass. I should say it's going to enter, oh yeah, I do say it, from the air at an angle of 25 degrees. And if they don't tell you it, you can assume that the angle is relative to the normal. So we want to find the angle of refraction and the wavelength of light in the quartz glass. So what we are given lambda 1 is 737 nanometers. And we're told that the angle of incidence is 25 degrees. We would like to find, we know N1 is air, so it's 1.00. We know N2 is 1.47. So what we're trying to find here is we're trying to find angle of refraction, so we'd like to find theta 2. We'd also like to find lambda 2. Now, based on wanting to find theta 2, if I want to find theta 2, I'm going to need a theta 1. And then I need another variable where I know both the incident and refracted components, which is going to be my index of refraction. So I want to use an equation that has theta 1, theta 2, N1, and N2. So for that, I'm going to use Snell's law, this version. So that's sine of theta 2 over sine of theta 1. That's going to be this N1 over N2. We're going to use that to find the angle of refraction. So sine of theta 2 is going to be this N1 over N2 times sine of theta 1. And we can calculate that. So we know N1 is 1. We know N2 is 1.47. We've been told that the angle of incidence is 25 degrees. So we're going to get that sine of theta 2 is about 0.2875. But that's sine of theta 2. I'm interested in theta 2 itself. So we're going to take the inverse, or that second function sine of that 0.2875. So we do that. We're going to get sine theta 2 is about 16.7 degrees. Now let's do a little bit of a consistency check. We're going from an index of we're going from a medium of low index to high index. So we should expect the angle of refraction to be less than the angle of incidence. 16.7 degrees is less than 25 degrees. So that's telling us that our light ray is bending towards the normal. That's good. So we know that this is 16.7 degrees. Now to find lambda 2, we have a lot of variables. This certainly opens up the playbook in which version of Snell's law we'd like to use. But again, we want to be careful about using calculated values to find more calculated values. So I'm going to pretend I didn't calculate theta 2. To find lambda 2, I have to pair up with lambda 1. And I need information about something that we know in the incident medium and the refracted medium, which is again our indices of refraction. So I want something with lambda 1, lambda 2, N1, and N2. So for that, what I'm going to actually have here is I'm going to have this other form of Snell's law. So I'm going to have this N2 over N1. This is equal to lambda 1 over lambda 2. Now my interest is to find lambda 2. So if I rearrange this, lambda 2 is going to be lambda 1 times N1 divided by N2. With Snell's law, you can be very forgiving with the units on things as long as like the core, like for example, like if I have lambda or the wavelength, whatever wavelength I pick for lambda 1, I have to keep that the same for lambda 2. So in this case, I know lambda 1 is in nanometers. If I keep that in nanometers in the equation, that's fine. I just have to understand that lambda 2 is going to come out in nanometers as well. But if you want to convert things to meters and all that, that's fine. But the units, again, are a little forgiving on this. So I have that wavelength of 737 nanometers. N1 is divided, N1 is, 1, and then N2 is that 1.47. So again, we have nanometers times no units times no units. So this is going to come out in units of nanometers. So I'm going to get that the wavelength is about 501 nanometers. Now, when we're going from a medium of low to high, we expect light to slow down, and we know from our universal wave equation, V equals F lambda, if light slows down, wavelength has to decrease. Well, we're going from 737 nanometers to 501 nanometers, so that's good. That is kind of consistent with the physics that we know. And that's pretty much the gist of Snell's law. But the next video, we're going to show you where Snell's law kind of falls into a little bit of a pitfall. So stay tuned.